Question number 66. Consider the situation shown in the figure. The width of each plate is B. The capacitor plates are rigidly clamped in the laboratory and connected to a battery of AMF epsilon. All surfaces are frictionless. Calculate the value of M for which the dielectric slab will stay in equilibrium. Here, this is dielectric slab. So let's consider that portion X of the dielectric is inside, or you can say that length X of dielectric is inside and portion L minus X of the capacitor is without dielectric. Now we find the capacitance. So capacitance of this portion having dielectric constant. So say C1 equal to epsilon naught K, length and breadth area is X into V. Here, width of each plate is V, so X portion is this and width is V. So Vx divided by separation is T. Now, the remaining portion has capacitance C2, that will be epsilon naught V times L minus X divided by T. These two capacitances are connected in parallel. So equivalent capacitance in parallel can be formed by adding the two epsilon naught KXB upon D plus epsilon naught B, epsilon naught B times L minus X upon T. So this will come out to be epsilon naught B upon T outside. Then from here, Kx, so currently finding Kx plus L minus X, which is equal to epsilon naught B upon D times L plus X times K minus 1. Now, if force applied by the battery on dielectric is F and it moves through distance dx, here we are considering the motion of this dielectric towards battery, then work done by the battery will be equal to change in energy of the capacitor plus work done by the force on the capacitor. So work done by the battery, if we denote as dWB, so it will be equal to charge supplied by the battery time charge multiplied by voltage. So charge is dq. Here, charge supplied by battery during this process dq times voltage of battery is V. But Q equal to CV, we know Q equal to CV. So dq will be dc times V. So we write this value here. So dc times V dot V, that is dcV square. So this is work done by the battery. Now change in energy of the capacitor. Change in energy of capacitor will be equal to capacitance DC and voltage V square. So 1 by 2 DC V square. Now, as I told you that this energy or work done by the battery dCV square will be sum of dCV square will be sum of change in energy of the capacitor, that is 1 by 2 dCV square plus work done by the force of the capacitor. So suppose force is F and it capacitor moves through distance dx. So F dx. So let's find out F dx. f dx will be equal to, here this is dcv square, this is half dcv square. So this will give half dcv square. So we write it as f equal to 1 by 2b square bc upon dx. Now let's write the value of dc, and dc we have found as epsilon naught b upon d times L plus x times k minus 1. Now, if we find dc upon dx from here, so dc upon dx, so here x will become 1, this will become 0. So it will be epsilon naught b times k minus 1 divided by d. So we have got the value of dc upon dx. So force from here will be F equal to half v square times dc upon dx. dc upon dx is epsilon naught b k minus 1 upon d. So, but f equal to mg. So here we write it as mg equal to this much 1 by 2 v square epsilon naught b times k minus 1 upon d. And our concern is to get m. So m will be equal to this, g will go in denominator. So v square epsilon naught b k minus 1 divided by 2 g d, which is our answer. Thank you for watching.